Is going to be a review over the concept of bond energy calculations. This is actually kind of a not super precise way of referring to this. This is really calculating the change in energy for a reaction, sometimes known as the change of enthalpy, although we haven't actually covered that term yet, but we will shortly. But we're going to use the concept of bond energy to determine if energy is absorbed or released in a chemical reaction, and we're going to try to estimate about how much energy. This is really an estimate. We're going to learn some more precise ways, both to talk about and to calculate this energy in the very near future, but this is an important conceptual step to getting there, so we do this first. All right, enough of me blabbing. Okay, so let's look at some simple reactions, thinking about like hydrogen atoms coming together, and because I like to think of this at the atomic level, we're going to think of some hydrogen atoms that are floating apart from each other, right? And they're going to come together to form hydrogen molecules, which are now going to have a covalent bond between them, as we talked extensively about last semester. And that formation of that covalent bond has an energy associated with it. Specifically, and this is going to feel backwards to you from things you may have learned either in high school or in other classes that weren't chemistry. When bonds form, energy is released. So this reaction of hydrogen atoms coming together, according to my bond energy chart over here on the right, and you're always going to be supplied a chart like this for doing these problems, by the way. But this tells us that this reaction is going to release 432 kilojoules for every mole of hydrogen 2 that gets created. All right. This is, again, going to feel backwards to some of you, but you have to take my word for it. When bonds are formed, energy is released. The reason for that is that the electrons in isolated atoms are higher in energy than they are when they form a bond. When they form a bond, the energy of those electrons is reduced, and that's where the energy comes from. So the potential energy of the electrons in the atom versus the molecule, it's lower in the molecule, so energy gets released. So if you go for my second example here, 2 oxygen atoms coming together to form oxygen molecules, remember that this oxygen molecule, when it forms, the Lewis dot structure looks like this, all right? And so there's a formation of a double bond present here. So when we go to our table, we're going to look at this O to O double bond, not the single bonded oxygens. We'll do an example with those later. Not the single bonded oxygen in this case. We're looking for the double bonded oxygen here. So this is going to release 498 kilojoules per mole. Kilojoules per mole. Incidentally, about the units, kilojoules is a unit of heat. It's thousands of joules. And a mole, of course, is our usual 6.02 times 10 to the 23rd, in this case, molecules. And so for every mole of O2 molecules that gets formed, 498 kilojoules of energy get released, generally speaking in the form of heat. All right, so if we go in the other direction, in my third example here, notice that we're going to go from oxygen molecules to oxygen atoms. So in other words, we had oxygen molecules to begin with, right? And we've now broken those up into lone oxygen atoms, separated, fully apart from each other, no longer covalent bonded. That's going to absorb 498 kilojoules per mole. Very shortly, we're going to start using plus and minus to talk about absorbed and released, but today we're just doing this, again, as conceptually as we possibly can. The way I remember this, because honestly, I still get tangled up on the absorbed release thing once in a while, especially if I haven't thought about it for a while, is that if you think about a covalent bond like 2 magnets stuck to each other, so in this case here with our oxygens, if you think of these having an attractive force between them, because that's what we mean by a bond, if you're breaking that bond, you're separating those atoms. So it's just like separating 2 magnets. You've got to put a lot of energy in to make that happen, right? If you've got 2, especially like those silvery neodymium magnets. If you got two of those stuck together, you've really got to pull those apart, right? That's putting energy in. So breaking a bond is pulling things apart, in this case, two oxygen atoms. If you're pulling them apart and they have an attractive force between them, as you pull them apart, you've got to put energy in to make that happen, right? And that's always how I keep it straight. It's a little harder conceptually to think about bonds forming. Again, as I mentioned earlier, it's potential energy of electrons, blah, 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 blah. If you just think of breaking bonds as pulling things apart, it's not like snapping a stick, right? Like that's the picture that gets in our heads from high school. So better to think of this as pulling things apart that are attracted to each other. If you're doing that, you're having to put energy in. That's going to absorb energy in as far as bonds breaking. Okay? All right. Try to keep that straight in your head. I know it's hard. All right. Let's do an example of what we can do, what the power of this estimation is. So we're being asked in this example to estimate the change in energy for a reaction using bond energies, and we've been provided the bond energies, as I promised we would be. And we're taking two hydrogen molecules, and if you'll recall, the Lewis dot structures for hydrogen look like that, and an oxygen molecule, and we're turning it into two waters. All right? Drawing the Lewis dot structures is actually the first step of every single one of these problems. If you're not real comfortable about Lewis dot structures, you can go back on my YouTube channel. There's more. There's an entire activity video in there about Lewis structures. Now would be a great time to review those. Okay. Sometimes I'm going to be nice and provide them to you. Sometimes I'm not, because you should know how to do a Lewis dot structure. Okay. So now let's look at how much energy is absorbed or released here. So we've got, over here, we've got two hydrogen to hydrogen bonds that are getting broken. And we have one oxygen double bond that's getting broken. So altogether, we have, pull out my calculator here, 2 times 432 plus 498. That gives us 1,362 kilojoules per mole. That's being absorbed, right? Because these are over here on the reactant side, right? We're going to break these bonds, right? So these bonds are getting broken in this process, right? We've got to separate the atoms just as though we were taking one set of Legos apart and putting them back together into something new. These over here on the product side, these are going to get formed, right? So now let's keep our colors consistent. Let's calculate how many we've got over here. Now notice we've got a coefficient of 2 waters. That's why I drew 2 of them. Each water has 2 O to H covalent bonds, right? So overall, you've got 4 those O to H bonds that are getting formed, right? So that's going to come out to be 4 times 4, 64. That's going to be 1,856 kilojoules per mole, and that's being released, right? So how much energy overall is being either absorbed or released? Well, the way you find that is you subtract these two. So we're going to do 1856 minus 1362. And I know some of you that learned this a different way are cringing right now, but just please stick with me for a minute. So we're going to subtract this, and we're going to get 494 kilojoules per mole. All right. Now the question is energy overall getting absorbed or released? Well, which one's bigger? The amount of energy that's absorbed or the amount of energy that's released by the formation of bonds? And there's more energy being released by the formation of bonds than there is being absorbed by the breaking of bonds. So therefore, this is the number of kilojoules per mole that are released, right? Because the amount that we release from formation is bigger than the amount of energy being absorbed by breaking bonds. All right, so that's how we're going to do these. This is a little different. Again, you may have learned an equation for this previously in your education, or you may not have, but it's going to confuse some folks later with another equation we're going to learn. Just remember, all I want you to do is understand the conceptual. Breaking bonds over here on the reactant side, that absorbs energy. Forming bonds over here on the product side, that's going to release energy. All right. So I'd like you to do a practice problem. So pause the video, get out a piece of paper, get out your pens and your pencils, Do this practice problem, restart the video, and then watch my solution for it. Okay, so somehow my instructions here got like really messed up. That I'm sure you've figured this out by now. Estimate the change in energy for the reaction using bond energies. I don't know what happened there, but that's okay. All right, so let's think about, and this is one you may have messed up because if you didn't do the Lewis dot structure, you wouldn't know that this is hydrogen peroxide. This is the only way to make this Lewis structure work out. There is no O to O double bond here. All right. If you did not pick up on this, feel free to pause the video again and go back and fix your numbers. It'll just take you a second. Over here, we've got two waters, and I really encourage you, even if you're drawing the Lewis structure, go ahead and draw it twice if there's two of them, just so that it helps you keep account of how many bonds you're dealing with. Okay. All right, so over here on the breaking side, you've got 2 of the O to O bonds that we're breaking, and we've got 4 of the O to H bonds that we're breaking, right? So that's going to be 280, and I guess I could have just done this in the calculator. I don't know why I'm writing it out. But anyway, 1856 plus the 280. So that's overall, we've got 2136 getting broken. All right. And remember, that's going to be absorbed because breaking bonds absorbs energy. And then over here on the formation side, what do we got? We've got 4 of the O to H bonds from the waters, which I happen to know is 1856. And then we have 1 of the O to O double bonds. So that's 1856 plus 498. So that's overall 2354 kilojoules per mole getting released. All right, so we're going to subtract those. 2354 minus 2136 is, so overall, if we subtract those, we get 218 kilojoules per mole. And because our released number is bigger than our absorbed number, that's overall energy getting released, right? So not as much being released in this reaction, still a little bit. 218 kilojoules per mole is quite a bit, but it's kind of modest, I suppose, for a reaction. Again, we're going to learn a more precise way to deal with this. There's tabulated values that are going to give us exact numbers for this, but these are pretty good estimates, and it gets across the most important thing, which is this business about breaking bonds absorbs energy, forming bonds releases it. Okay, we're going to come back to this conceptually over and over and over. So try your best to get this straightened out in your head. Write yourself a little post-it, put it on the front of your course packet or your binder or whatever, yeah, try to get that through your head. All right, post any questions in the comments or get in touch. Hope you have a great day. Bye-bye.